Hi, welcome to the video 3 for the equations course. So this video is about problem solving with theory of equations. So what we will do here is we'll look at a lot of problems and also a couple of theorems on the way, which will help us understand how we go about solving many types of equations. So the target audience for this is anybody preparing for PRMO, RMO, INMO, and JEE Advanced. So by the end of this video, you should feel fairly comfortable solving any questions here in equations. So I want you guys to pay attention and go through the problems as I am solving it. This will be a slightly long session because I'm going to discuss a lot of problems, and please take your time and you can pause the video, rewind, go back to previous questions and do it again. So it might take multiple sessions for you to cover the whole video, but definitely pay attention to this video. I will discuss enough problems and enough type of problems to cover all possible questions that might come in these sort of exams. So we will also basically realize that whatever we have learned about equations so far and the few theorems that we'll discuss today are going to be sufficient for solving any PRMO, RMO, or even INMO question if it comes to that. And JEE Advanced obviously falls in that category as well. So here we go. So this is the first question. Show that all the roots of this equation are real, given that these constants small a1 to small ah and capital A1 to capital AH are real numbers, right? So what we will do here is first we'll realize what kind of a polynomial equation this is. So what we can do is multiply both sides of the equation by x minus a1, x minus a2, and so on till x minus ah in order to remove the fractions. So if we do that multiplication, we get something like this: a1 square x minus a2 to x minus ah plus a2 square x minus a1, and the missing factor is x minus a2. So we'll start with x minus a3 here till x minus ah, and so on. You'll get terms till ah square x minus a1, so on, right, is equal to k times x minus a1, x minus a2 till x minus ah. So what I'm doing is multiplying both sides by this. Now you'll realize that you don't have to actually expand this, and even just by thinking about it, you will realize that this will be an equation that will have all the coefficients of this equation, all the coefficients of this polynomial a of this polynomial p of x, let's say, will be real. Why will the coefficients be real? Because all of these numbers a1, a2 till and capital A1 to ah, right, all of those are real. So therefore the product is also real, k is also real. So therefore whatever this equation will be will have all coefficients real. At this point we have to understand one particular theorem which says that if all the coefficients are real in any polynomial, all the coefficients are real, then imaginary roots or complex roots will occur in pairs, right? Complex roots will occur in pairs. So what sort of pairs? So if one root is x plus iy, then the another root will be x minus iy, right? Why is that supposed to be true? Because if they don't occur in pairs, then the sum of the roots will be imaginary, right? The sum of the roots is this coefficient. By Vieta's relation, we have sum of the roots is minus an minus 1 by an. And since an minus 1 and an are purely real, therefore the sum of all the roots must also be purely real, right? Now that cannot happen if you have one root like 2 plus 3i and if there is no root like 2 minus 3i, then that will not happen. So you have to have conjugate roots here. So we'll use this theorem and we'll prove by contradiction. So let's see how we will do that. So what we will do is let's assume that alpha plus I beta is a root, and this is basically a complex root of the equation given to us, right? The equation given we'll write in the original form itself. So this is my equation. Plus AH square by X minus AH is equal to Q is equal to K. So if this is a root, we are assuming the opposite. We want to prove that all roots are real. So we are assuming the contradiction that there is a root like this. Therefore, by the theorem, we also know that alpha minus I beta is also a root of this equation. Right? So what I will do is I will put alpha plus I beta for X everywhere. And then I will put alpha minus I beta for X everywhere. So I get equations like this: A1 square by alpha plus I beta minus A1 plus A2 square by alpha plus I beta minus A2, and so on till AH square by alpha plus I beta minus AH is equal to K. And the second equation that I get is A1 square by alpha minus I beta minus A1 plus A2 square by alpha plus alpha minus I beta minus I beta minus A2 plus so on till AH square by alpha minus I beta minus AH, right, is equal to K. These two are valid equations because if this is a root, by assumption, this is also a root. Now what you have to do here is just subtract these two equations, right? If you subtract these equations, what we get is A1 square 1 by alpha plus I beta minus A1 minus 1 by alpha minus I beta minus A1, right? And you get similar terms, right? A2 square by 1 by alpha plus I beta minus A2 minus 1 by alpha minus I beta minus A2. And you get similar such terms is equal to 0, right? After subtracting these two, this is what I'm supposed to get. Now let's simplify this fraction a little bit and we'll understand what is happening. So I'll do it on the next screen. So we have A1 square 1 by alpha plus I beta minus A1 minus 1 by alpha minus I beta minus A, right? I want to simplify this, right? So I can just take it as a product here and say that it is alpha minus A1 minus I beta multiplied by alpha minus A1 plus I beta. This is the product, and on top it will become alpha minus I beta minus A1 minus alpha minus I beta plus A1, right? So what is coming here? This is A minus B into A plus B. So denominator becomes A square minus B square. A alpha minus A1 whole square minus I square B square becomes plus beta square, right? Numerator becomes, this cancels with this cancels with this. You get minus 2I beta, right? Minus 2I beta. And outside there is A1 square, right? So this is my first bracket, right? Now think about it. You get similar brackets everywhere, right? So I will just write the final equation that I will get 2I beta minus 2I beta A1 square by alpha minus A1 whole square plus beta square minus 2I beta A2 square by alpha minus A2 whole square plus beta square, and so on, so on. You keep getting these terms. Every term is a negative term, and this is equal to 0. So minus 1 I can cancel, and I get an equation like this: 2I beta A1 square by alpha minus A1 whole square plus beta square plus A2 square by alpha minus A2 whole square plus beta square plus so on, so on. This is equal to 0. Now think about it. Since A1, small a1, all of this are real numbers, this quantity denominator is positive because it's a sum of two squares, and numerator is also positive. So you get this entire term is positive, and similarly every term inside is positive. So this whole bracket is going to be positive, and you have 2I beta multiplied by something positive is 0, which implies that beta must be 0, right? And beta must be 0 means that alpha plus I beta is becoming a real root, right? Because if beta is 0, then imaginary part has disappeared and that is a real root. So this contradicts our assumption that alpha plus I beta was an imaginary root. So whenever you have an imaginary root here, you will always get beta is equal to 0. So that means that all the roots of this equation are real. So what did we use to solve this problem? We used our basic understanding of equations, where we knew that if an equation has all real coefficients, then imaginary roots will occur in pairs. After that, it was just us doing a proof by contradiction, where we assume one complex root and we get its conjugate complex number also as a root of the equation. Once you do that, you subtract and you will get that beta is equal to 0, which proves that the original alpha plus I beta was real, right? So this is the first question. The next thing that I want to look at is a theorem actually, which is quite famous. It's called the rational roots theorem. Rational roots theorem. So what is this theorem saying? It says that if the rational number p by q, where p and q are in lowest terms, so basically have no common factors, basically p and q are co-prime. If this is a root of the equation, a0 x power n plus a1 x power n minus 1 plus so on till an is equal to 0, right? Where a0, a1 and an are integers, and a0 is not equal to 0. So we have an nth degree equation. A0 is not equal to 0. All the other coefficients are integers. And we are saying if the rational number p by q is the root of this equation, then we can show that, we can say that p is a divisor of an and q is a divisor of a naught. So basically we can prove that p divides an and q divides a naught if we have p by q as a root of this equation with all integer coefficients, right? So the proof of this is not very hard. We'll quickly discuss it. So let's put p by q inside this, p by q power n plus a1, p by q power n minus 1 and so on, and plus an is equal to 0. This should be true. So multiplying throughout by q power n, you'll get a naught pn plus a1 pn minus 1 q plus so on plus an q power n is equal to 0, right? Now you take a naught pn to the other side, so you'll get a1 p power n minus 1 q plus so on till an qn is equal to minus a naught p power n, right? Now you can say that this side is divisible by q because every term has a q, and this side should also therefore be divisible by q. And since p and q have no common factors, q must divide a naught, right? Q must divide a naught, we get immediately. Correct. So we can also solve it in a different way and say that we will transpose this term to the right side, right? So we'll get a naught p power n plus a1 p n minus 1 q and so on till a n minus 1 p q n minus 1 is equal to minus a n q n. And now you can prove that the left hand side is divisible by p because every term has a p. So the right hand side must also be divisible by p. And again, because p and q are in lowest terms, p must divide an. So it's a very simple proof by divisibility that p must divide an and q must divide a naught, right? So that is the rational roots theorem. A corollary of this theorem is the next theorem, which says, if I have an equation like this, x bar n plus a1 x bar n minus 1 plus so on, plus an is equal to 0. So now this is a monic polynomial, which we discussed earlier. Monic polynomial is a polynomial with the leading coefficient being 1, right? Now each a1 to an here is an integer. a1 to a2 still an belongs to z integers, right? So now we can say that every rational root of this equation must be an integer. Also, every such root must be a divisor of an. How are we making these claims? We are following the previous theorem only. So we are saying if p by q is a root of this, then that means that p should divide an and q should divide a naught, right? But here, since therefore a naught is 1 implies q divides 1, that implies that q must be 1, right? Q must be 1 means p by q is an integer, right? And if p by q is an integer, then p divides an, right? That also we have. So here, if you have an equation like this with integer coefficients here, then every rational root will be an integer and all of those integers will be divisors of an. So this theorem combined with the previous theorem will help us solve many problems. An example problem is this, question number 2 for us. So find the rational roots of the equation x power 4 minus x cube minus 19x square plus 49x minus 30 is equal to 0. So this fits the pattern that we had in the previous theorem, where first coefficient is 1. So every rational root of this must be an integer and all of those roots must be divisors of minus 30, right? All roots are divisors of the last coefficient. All the roots divide minus 30. Therefore, what are the divisors of minus 30? You can get plus minus 1, plus minus 2, plus minus 3, plus minus 5, plus minus 6, plus minus 10, plus minus 15, plus minus 30, right? So these are the possible roots. These are the possible roots of it, possible integer roots. Now, you can quickly check, you can start checking from plus minus 1 and you will easily recognize that x is equal to 1 and x is equal to 2 will be roots of this equation, So then what follows from that is that x minus 1 and x minus 2 are factors of this, correct? So we can quickly factorize this now. We can say x cube x minus 1, right? Or I'll actually do it in a different way. I'll just say x cube x minus 1 minus x cube plus x plus I need a minus 19x square. So I'll do minus 19x x minus 1. I have a plus 19x, so I need to do plus 30x minus 1. Notice that this is a factorization. It becomes x square 4 minus x cube minus 19x square plus 19x plus 30x minus 30. So I'll take this out and it becomes x cube minus 19x plus 30. And I know that x minus 2 is also a factor. So 2 cube is 8. 8 minus 38 is minus 30 plus 30, right? So I will factorize it once more. So what I will do is x square x minus 2 minus 2x square, so I have to do plus 2x x minus 2, so minus 4x, so I have to do plus, but actually minus 15 x minus 2. So basically I get x minus 1, x minus 2, and x squared plus 2x minus 15, right? So I have two integer roots, 1 and 2, and here I will have irrational roots, I think. Or maybe this is also factorizable actually. Yeah, this is also factorizable. It is plus 5 minus 3, right? So I will get x plus 5, x minus 3 as factors for this. So I'll get 4 roots, minus 5 and 3. I found all the roots. So it was crucial to use the theorem and know that all my rational roots will divide minus 30, and also that all my rational roots are actually integer roots. So here we have applied the previous two theorems that we saw, right? Let's move on to the next question. The next question for us is this one, question number 3. This is if the sum of two roots of the equation 4x power 4 minus 24x cube plus 31x square plus 6x minus 8 is equal to 0, be 0. Find all the roots. So basically we are looking at a 4th degree equation, but we are given some condition, right? So we are going to utilize that condition to somehow solve it, right? So let the roots be alpha, beta, gamma, delta, right? These are the roots. Then sum of the roots is what? We get alpha plus beta. By Vieta's relations, we get this. This is equal to 6. We get alpha, beta. Sum of the roots taken 2 at a time, alpha, beta, plus gamma, delta, plus alpha, gamma, plus alpha, delta, plus beta, gamma, plus beta, delta. These roots are equal to, this is equal to 31 by 4. Minus 20, minus of minus 24, this is minus of minus 24 by 4. And this is plus of 31 by 4. That's why it is coming. So you should be familiar with Vieta's relations. Then we get 3 at a time, right? 3 at a time product of the roots, right? So what we can say is alpha, gamma, delta plus beta, gamma, delta plus alpha, beta, gamma plus alpha, beta, delta. These should add up to minus 3 by 2 because you'll get minus 6 by 4. And finally, you have alpha, beta into gamma, delta is equal to product of roots taken 4 at a time will be equal to minus 2, right? These relations are available to us. We are also given an additional information that sum of 2 of the roots is 0. So let's assume that alpha plus beta are those roots and alpha plus beta is equal to 0. This is what is given to us, right? So now let's try to simplify this. From here, from this equation, we get, since alpha plus beta is 0, we get gamma plus delta is equal to 6, right? Great. Now this equation, let's try to work on. Let's try to work on this one. So here, if you notice, I can factorize this in a nice way. So what I can say is alpha, beta plus gamma, delta plus, I can take alpha common here and beta common here. So I'll get alpha, gamma plus delta plus beta, gamma plus delta, right? So I can write this as alpha, beta plus gamma, delta plus alpha plus beta common, gamma plus delta is equal to 31 by 4. Now, because alpha plus beta is 0, what we get is this term disappears. So we have alpha, beta plus gamma, delta, right? We have alpha, beta plus gamma, delta is equal to 31 by 4. Correct? Okay. Now, alpha plus beta is 0. Again, we'll use that. So in the third one, what to do here? So again, here, what we can do is take common gamma delta common here, gamma delta common here. So I'll get alpha plus beta, gamma delta alpha plus beta plus alpha beta common here, alpha beta, and you get gamma plus delta is equal to minus 3 by 2, right? Now, since this is 0, this term vanishes, and gamma plus delta is equal to 6. So we get 6 alpha beta is equal to minus 3 by 2. Therefore, we get alpha beta is equal to minus 1 by 4, right? And if alpha beta is minus 1 by 4, then gamma delta will be 31 by 4 minus alpha beta will be 31 by 4 plus 1 by 4. So it is 32 by 4 or 8, right? We get gamma delta is 8. Great. Now, basically gamma delta is coming 8 and alpha beta is coming minus 1 by 4. So also alpha plus beta is equal to 0. Alpha plus beta is 0 and alpha beta is minus 1 by 4. That immediately gives us the value. So alpha is equal to minus beta, therefore minus beta square is equal to minus 1 by 4. So beta can be plus minus 2, plus minus half, right? So alpha beta are plus minus half, we have gotten plus minus half. And notice that now you have gamma plus delta is 6 and gamma delta is equal to 8, right? So obviously this will be 4 and 2, right? So gamma delta could be 2 comma 4. So the roots of our equation, we have found all 4 of them, plus minus half and 2 comma 4. So notice here, what was the trick of solving this? We had this condition, right? So we have to use this condition intelligently. So what was so intelligent about our use of this condition? We grouped these two together and these two together. We got this, right? Then here again, I took factors nicely by taking alpha common here and beta common here, and therefore writing it as alpha plus beta into gamma plus delta, because I know alpha plus beta is 0. I did the same thing here also. I did gamma delta common and alpha plus beta came as common, and the remaining was alpha beta into gamma plus delta. So if you factorize and group the terms correctly, then that helps in getting the answer quickly, right? So I hope that is something that you will keep in mind while solving your own questions. The next one that we look at is this. Question number 4 for us is basically if alpha, beta, gamma are roots of the equation x cube plus qx plus r is equal to 0, we have to prove that alpha power 5 plus beta power 5 plus gamma power 5 by 5 is equal to alpha cube plus beta cube plus gamma cube by 3 multiplied by alpha square plus beta square plus gamma square by 2. So now there is a way to solve this by doing the Newton's identities, which are recursive identities. There is a video on my channel which covers Newton's identities in detail. So that will help you find alpha power 5 plus beta power 5 plus gamma power 5, which is basically simply S5. And similarly S3 and S2, right? We can do it using that, but I am not going to use that right now, assuming that you don't know Newton's identities. So how will we prove it otherwise, right? So basically what we do is, since alpha, beta, gamma are roots of this equation, we can write alpha q plus q alpha plus r is equal to 0, beta cube plus q beta plus r is equal to 0, and gamma cube plus q gamma plus r is also equal to 0, right? So if I add all of this, what I will get is summation of alpha cube plus q common summation of alpha plus 3r is equal to 0. What do I mean by this? What I mean is alpha cube plus beta cube plus gamma cube plus q alpha plus beta plus gamma plus 3r is equal to 0, right? Now, in the equation, if you notice, if alpha, beta, gamma are the roots, alpha plus beta plus gamma by Vieta's relation is 0, because there is no x square term here. So therefore this term vanishes, right? So what we get is summation of alpha cube, or basically alpha cube plus beta cube plus gamma cube, is equal to minus 3r, right? This we have gotten. Now summation of alpha square, basically what is that? Alpha square plus beta square plus gamma square will be equal to alpha plus beta plus gamma whole square minus 2 times alpha beta plus beta alpha beta gamma plus alpha gamma, right? This is a basic identity, and since this is equal to 0, alpha plus beta plus gamma is 0, so this becomes 0 minus 2 times. What is sum of the roots taken 2 at a time here? Sum of the roots taken 2 at a time in this equation is minus plus, so it is q only, right? This becomes minus 2q. So therefore we have summation of alpha square is minus 2q, summation of alpha cube is equal to minus 3r, right? So these things we have already found out. So basically we know everything here, right? The only thing that we are left to find out is what is summation of alpha power 5, right? Which is basically alpha power 5 plus beta power 5 plus gamma power 5. So how do we do that? Again, we'll use the equation that we have, okay? So I'll do that in the next page. So suppose you have this equation, x cube plus qx plus r is equal to 0, right? So multiply both sides of this equation by x square. We'll get x power 5 plus qx square plus qx cube plus rx square is equal to 0, right? This is an equivalent equation. Now, obviously, x is equal to alpha, beta, gamma was satisfying this equation. So it should satisfy this equation also, right? So therefore, we have alpha power 5 plus q, alpha power 3 plus r, alpha square is equal to 0. Similarly, beta power 5 plus q, beta power 3 plus r, beta square is equal to 0. And gamma power 5 plus q, this is also equal to 0. So adding all of them, if you add, you get alpha power 5 plus beta power 5 plus gamma power 5 is equal to basically minus q, alpha power cube plus beta power cube plus gamma power cube minus r, alpha square plus beta square plus gamma square, right? And earlier we have already derived what is alpha cube plus beta cube plus gamma cube. That was equal to minus 3r. And what was alpha square plus beta square plus gamma square? That was equal to minus 2q. So here what we get is 3qr minus or plus 2qr. So we get basically 5qr, right? 5qr is the value of this powers. So we have found this also. Now basically what we have to prove is 1 by 5 summation of alpha power 5 is equal to summation of alpha cube by 3 into summation of alpha square by 2. So what is this? 5qr by 5 is LHS, and this is minus 3r by 3, and this is minus 2q by 2. So this becomes minus minus, this is qr this side, and this is also qr. So we have proved the problem. So basically the idea was, without using Newton's identities, I have found all my things. I have found alpha power 5 plus beta power 5 plus gamma power 5. Notice the way in which I found it. Pause the video, go back and see how we did it. That will help you in future problems when you are faced with something similar, right? Okay, let's move on to the next question. This is question number 5. Question number 5 says, if alpha, beta, gamma, delta are roots of the equation x power 4 plus px cube plus qx square plus rx plus s is equal to 0. Show that 1 plus alpha square multiplied by 1 plus beta square multiplied by 1 plus gamma square multiplied by 1 plus delta square. Show that this product is equal to 1 minus q plus s whole square plus p minus r whole square. You have to basically find out this thing, right? So since alpha, beta, gamma, delta are roots of this equation, we can write the polynomial this px cube plus qx square plus rx plus s also as x minus alpha, x minus gamma, x minus delta, right? This is true. Now notice that how will we get ever a product of alpha square plus 1, right? It can be written as alpha square plus 1 is equal to alpha square minus I square, right? Because I square is minus 1. So this is basically alpha plus I into alpha minus I, correct? So every term is like that. Beta square plus 1 is equal to beta plus I into beta minus I. So every term is fitting that pattern. So all we have to do here is substitute x is equal to I and x is equal to minus. So we have something like this and something for the delta term also. Therefore, putting x is equal to I, what do we get, right? So we get here I power 4 is 1 plus pi cube is minus I, 1 minus pi plus q into minus 1 plus ri plus s is equal to I minus alpha, I minus beta, I minus gamma, I minus delta. And now you put x is equal to minus I. So that will be 1. And minus I cube is minus I cube. So that is equal to plus I. So 1 plus pi. And this is going to be plus q into minus 1. This is going to be minus ri plus s. And that will be minus I minus alpha, minus I minus beta, minus I minus gamma, minus I minus delta. Now multiplying these two, multiply these two equations, what we get is you can take minus common from each of these terms, put it inside that. So it will become alpha plus I into alpha minus I, which is the same thing that we are getting. So this multiplication of right hand side here becomes the left hand side of the original equation. So it will become 1 plus alpha square, 1 plus beta square, 1 plus delta square, and 1 plus gamma square, right? So all we have to do is multiply this side to get the answer. What is this side? It is actually 1 minus q plus s plus r minus pi multiplied by 1 minus q plus s minus r plus p. So minus of r minus pi, right? So this is your first term, which is a real part, and this is imaginary part, the same real part and then minus. So it is just going to be basically a plus bi into a minus pi is a square minus a square plus b square. So that's why the answer is this square plus this square, which is what is this, right? So I hope you understood this video. Pause, work it out if you are a little confused. You have to substitute x is equal to I and x is equal to minus I only because we realize that 1 plus alpha square is basically the factorization is alpha minus I into alpha plus I. And that will come if you put in this expression x is equal to I and x is equal to minus I. Eventually you have to multiply those, right? So I hope that is clear. The next question for us is question 6, which is again similar to the Vieta's relation question that we just now did. Question number 4, I think it is similar to. So it's given if alpha plus beta plus gamma is equal to 1, alpha square plus beta square plus gamma square is equal to 2, right? And alpha cube plus beta cube plus gamma cube is equal to 3. Then we have to find the value of alpha power 4 plus beta power 4 plus gamma power 4. So this is very similar to question number 4. So what we will say is we will first step is determine the equation whose roots are alpha, beta, y, gamma, whose roots are alpha, beta, gamma. And the second step is find alpha power 4 plus beta power 4 plus gamma power 4 in that equation, right? So first we are going to try to determine that equation. So let's assume the most general possible fourth degree equation or third degree equation for these alpha, beta, gamma. So it is x cube plus px square plus qx plus r is equal to 0. Let this be the equation with roots alpha, beta, gamma. So you have alpha plus beta plus gamma is equal to minus of p, correct? And alpha beta plus beta gamma plus alpha gamma is equal to plus q, and alpha beta gamma is equal to minus r. These are Vieta's relations, but we already know alpha plus beta plus gamma is 1. Therefore, p is equal to minus 1 we get, right? Also, we can put the identity alpha plus beta plus gamma whole square is equal to summation of alpha square plus 2 times summation of alpha beta. Therefore, this part is 1 and is equal to summation of alpha square plus beta square plus gamma square is equal to 2, right? Because that is given to us here. So plus 2 into this summation is equal to q. So therefore, you get q is equal to minus 1 by 2, right? Q is minus 1 by 2. So we have already found P and Q here, right? Great. Now looking at my original equation, I have the results alpha cube plus P alpha square plus Q alpha plus R is 0, right? Because I'm putting alpha in the original equation. Similarly, if I put beta cube plus P beta square plus Q beta plus R is also 0. And similarly, gamma cube plus P gamma square plus Q gamma plus R is also 0. If I add these three relations, I get this cube summation of alpha cube plus P into summation of alpha square plus Q into summation of alpha plus 3R is equal to 0, right? I get this. So we already know this is 3. We know summation of alpha square is actually 2, so 2P, and summation of alpha is 1, so Q plus 3R is equal to 0, right? So now we get the value of R also because we have already figured out P and Q, right? So 3 plus 2P is minus 2 and Q is minus half is equal to minus 3R. So this becomes 1 minus half. 1 minus half is equal to minus 3R. So half is equal to minus 3R. Therefore, R is equal to minus 1 by 6, right? So what is R for us? R is the product here. R is the product here. Now basically we have found the equation, right? So let's write our equation in the next page. So our equation becomes x cube plus px square, and p is minus 1, plus qr, q is minus half, and plus alpha beta gamma, which is minus 1 by 6, is equal to 0. This equation has roots alpha, beta, gamma, right? So what do we do to get alpha power 4 plus beta power 4 plus gamma power 4? We already know what summation of alpha cube is, right? Summation of alpha cube we already know, that is equal to basically 3, right? That was, I think, 3 in the previous equation. Okay, that was given in the problem statement itself, that this was 3. So to get this, what I have to do is multiply this equation by x. What that does is makes it a fourth degree equation like this, minus 1 by 6x, right? Now, since the third degree equation has roots alpha, beta, gamma, obviously fourth degree equation will also have roots alpha, beta, gamma. So you'll put alpha power 4, beta power 4, gamma power 4 minus alpha power cube minus beta power cube minus gamma power cube minus half alpha square minus half beta square minus half gamma square minus 1 by 6 alpha minus 1 by 6 beta minus 1 by 6 gamma is equal to 0, is equal to 0, is equal to 0. Because alpha, beta, y, gamma will satisfy this equation also after multiplying by x. So adding this, we get summation of alpha power 4 minus summation of alpha power cube minus half summation of alpha square minus 1 by 6 summation of alpha is equal to 0. So this summation is what is asked in the problem. So this is equal to summation of alpha cube plus half summation of alpha square plus 1 by 6 summation of alpha. The summation of alpha cube is 3. Half into summation of alpha square is basically 2, I think. Alpha square plus beta square plus gamma square was given as 2 plus 1 by 6 into this is 1. So this is basically 4 plus 1 by 6, which is equal to 25 by 6. So we have found our answer. We have found our answer. So remember this trick that if you have some powers of alpha, right? So S5 suppose you have x power 5, alpha power 5 plus beta power 5 plus gamma power 5. And suppose you have to get to x power 7, right? Alpha power 7 plus beta power 7 plus gamma power 7. So multiply the whole equation by x square and substitute alpha, beta, gamma, right? To get to a higher power. We have already used this trick 2 times now. In the question number 4 also we used it, and now here in question number 6 also we are using it to show, right? I hope you understood this one. We'll move on now. The next question for us is question number 7, which is a slightly different sort of equation. So it's a simultaneous equation system. We have solved x plus y, x plus z is equal to 15. And then we have y plus z, y plus x is equal to 18. And finally, you have z plus x and z plus y is equal to 30. You have to solve this system of equations for x, y, and z. So the most obvious substitution here is, let's say x plus y is equal to capital Z, y plus z is equal to capital X, and z plus x is equal to capital Y, right? So using these substitutions, my equations become yz is equal to 15, zx is equal to 18, and xy is equal to 30. So multiply all 3 equations together, you will get x square, y square, z square is equal to 15 into 18 into 30. And therefore xyz should be plus minus root over this. Now what is the root of this? This will be 15 into 30. Okay, so 5 into 3 into 5 into 6 into 6 into 3. Okay, so it will become 5 into 6 into 3 plus minus 90. XYZ is coming out to be plus minus 90. So let's do 2 cases. One case is XYZ is equal to 90. In that case, what we get is we will divide XYZ by YZ. So you'll get X is equal to 6 and you will get Y is equal to 5 and Z is equal to 3, which will give us the equations Y plus Z is equal to 6, Z plus X is equal to 5, and X plus Y is equal to 3. Now solving this is very easy. Add up all of them, you'll get 2x plus y plus z. That will be basically 14. So x plus y plus z will be 7. So therefore x must be 1. Y plus z is, so z must be 4 and y must be 2. So we get one set of solutions. If you take x, y, z is equal to minus 90, you can similarly solve and get the other set of solutions. I will just write the answer here. X is equal to minus 1, y is equal to minus 2, and z is equal to minus 4. That is the other set of solutions following the exact same method. So this type of simultaneous equations and all, mostly there will be a nice substitution that will make it easier. So we did that substitution here, and the trick after that was multiplying and taking square root, right? Okay, let's go on to the next one. Let's take question number 8. Question number 8 for us is x square plus xy plus xz is equal to minus 12. The next one is y square plus yz plus yx is equal to 30, z square plus zx plus zy is equal to 18. We have to again solve for x, y, and z. So if you notice here, again, it is about noticing the pattern. You can take x common here. So it will be x into x plus 5 plus z is equal to minus 12. And this will be y into x plus y plus z is equal to 30. And this will be z into x plus y plus z is equal to 18, right? So if you add all three equations, you will get x plus y plus z common into x plus y plus z, which will become 30 plus 18 minus 12. So that is 36. Therefore, x plus y plus z could be plus minus 6. Once you got that, you will be able to solve for each of the things. You can put plus minus 6 here, you'll get x as plus minus 2, and you can basically solve this equation. So I'm just giving this as an example of the type of tricks that you need to see. You need to see this factorization, and then the best way to do it is not do anything weird now, just add, because you can take common x plus y plus z here. So that was an easy one. Let's look at another problem. Question number 9. Again, we have to solve a system of equations. We have y square plus yz plus z square is equal to 19 y square plus x square plus xy is equal to 49, and we have z square plus zx plus x square is equal to 39, and we have to solve this system of equations again, right? Take a moment, think about what you will do here. Adding and all doesn't seem to help here. So because adding is not giving us anything nice, so what I will assume is we'll probably have to subtract. So let's subtract. Let's subtract this. Let's call it 1, 3, 2. So what I will do is one minus 3. 1 minus 3 I will do. So 1 minus 3 if I do, I get y square minus z square plus yz minus zx plus z square minus x square, right, is equal to minus 20. That is what I get first. So here obviously z square gets cancelled, and you end up with y square minus x square plus z common y minus x minus 20. So my factorization is y minus x and y plus x plus z is equal to minus 20. Okay, so I will follow a same pattern and do another subtraction. So I will subtract, I will do 3 minus 2. If I do 3 minus 2, I should get z square minus y square, x square will cancel, plus zx minus xy. So x, z minus y is equal to minus 10 now. So this will become z minus y common. You will get z plus y plus x is equal to minus 10, right? Now we can immediately divide. This can be called as 4. This can be called 4. And this can be called as 5. So we can divide 4 and 5. So 4 by 5 basically gives us y minus x by z minus y is equal to 2. So that implies x is equal to 2z minus 2y, and this comes this side. So 3y minus 2z. X is equal to 3y minus 2z is coming. Correct? Okay. Now, this is my 6. Then, what should I do now? Now, I can substitute this 6 into the one equation in any one equation. So I'll substitute this 6 into this one. And let's see what happens. So we get y square plus x square is 9y square plus 4z square minus 2 into 3 into 2, 12yz plus x into y. So 3y square minus 2yz is equal to 49. So what I'm getting is 10y square plus 3y square. So 13y square plus 4z square minus 14yz plus 4z square is equal to 49. I'm getting. Okay. Okay, I will just do it on the next screen. So we have our original equations like this: y square plus yz plus z square is 19, let's say, and we have z square plus zx plus x square is equal to 39, and we have x square plus xy plus y square is equal to 49. These three equations are there. Then we also got basically y minus x, x plus y plus z is equal to minus 20. We got z minus y, x plus y plus z is equal to minus 10. We got x is equal to 3y minus 2z. And if we put this in the second equation, x is equal to 3y minus 2z, right? So what we'll get is z square plus z into 3y minus 2z plus 3y minus 2z whole square is equal to 39. So what this becomes is z square plus 3yz minus 2z square plus 9y square plus 4z square minus 12yz is equal to 39. So this becomes minus plus 5 minus 2, so 3z square, and plus 3yz minus 2, so minus 9yz plus 9y square is equal to 39. So dividing by 3, we get 3y square minus 3yz plus z square is equal to 13. We get this, and we also know that y square plus yz plus z square is equal to 19, right? Correct. Great. So fine, we have to solve these two equations. So how will we solve this? We have to solve these two equations for y and z, or at least get a ratio of y and z. So what we can say is 13 into 19 will be equal to 13 into 19 on both sides. So I will put 13 here as this expression. So I will get 3y square minus 3yz plus z square multiplied by 19 should be equal to 19 here as this expression. So 13 into y square plus yz plus z square, right? So what I get here is 57y square, 57y square minus 57yz plus 19z square is equal to 13y square plus 13yz plus 13z square. So that simplifies as 44y square minus 57yz. Okay, this is yz. So minus 70yz plus 19z square plus 6z square is equal to 0. So this becomes 22y square minus 35yz plus 3z square is equal to 0. 22 minus 35 plus 3. So 66 here, and I'm doing middle term factors. So 66, how can I do? 33 and 2, yeah. So I'll get 22y square minus 33yz minus 2yz plus 3z square is equal to 0. And solving it, I will get 2y minus 3z as factor, and the other side I'll get 11y minus z as factor. So from here I get the result that 2y is equal to 3z or z is equal to 11y, right? So if I put z is equal to 2y by 3 in the first equation, z is equal to 2y by 3 in the first equation. So what I will get is y square plus y into 2y by 3. So 2y square by 3 plus 4y square by 9. So that becomes basically 4y square plus by 9 plus 6y square plus 9 by 9 plus 9y square by 9. So 4 plus 6 plus 9, 19y square by 9, right? Is equal to 19. So you'll get y square is equal to 9. And by solving, you'll get y is equal to plus minus 3. How do I get this? I'm putting this value in this equation. And I calculated it in my head. So I'm getting y is equal to plus minus 3. If y is equal to plus minus 3, you will get z is equal to plus minus 2. Z is equal to plus minus 2 in that case. And once you get y and z, you can get x, right? So you'll get one set of solutions. We'll get x is equal to plus minus 5. One set of solutions for this case. And the other set of solutions will come when you put z is equal to 11y. You can put that in again in 1. Put z is equal to 11y in 1. You will get some root solutions. So eventually it can be solved now. So notice what are the steps involved. We had this set of equations. We subtracted 2 at a time, got this relations by then dividing. Once we got this, we substituted this back in one of the equations. We got another result like this. This result is looking like the first result here. So first result was yz terms and that was 19, and this is yz terms and that was 13. And then I combined both those relations like this, because 13 into 19 will be 13 into 19. So here I am putting 13 as this and 19 as a number. Here I'm putting 19 as this and 13 as a number. And that gave me one final equation that I had to solve, which was easily factorizable. I got this equation which I factorized and solved, right? Once we got that, we are near the end of the solution because we got two solutions, 2y is equal to 3z or z is equal to 11y. Put it back in any of the equations, ideally the first equation, and you'll get two sets of solutions, right? Okay. So that was that. That was a little trickier than the previous systems of equations that we were seeing. Let's go ahead. This is question number 10. To solve, again, a system of equations, you have x cube plus y cube plus z cube is equal to a cube. You have x square plus y square plus z square is equal to a square. And you have x plus y plus z is equal to a. You have to solve this system of equations. Great. So now let's look at this and combine it. So we can say that x plus y plus z whole square is equal to x square plus y square plus z square. X square plus y square plus z square plus 2 times xy plus yz plus zx, right? So since x plus y plus z is a, so this is a square and this is also a square plus 2 times summation of xy. So that implies that summation of xy, or basically xy plus yz plus zx, is equal to 0. That is an important result that will come in handy. Now from the first equation, right, we have an identity. This is a standard identity that everyone should be aware of. This identity says that it is equal to x plus y plus z multiplied by x square plus y square plus z square minus xy
minus zx minus yz. So from the first equation here, we know that this is a cube, this part is a cube, so a cube minus 3xyz is equal to x plus y plus z is a, this part is a square minus this part is 0, right? So it is equal to a cube, right? So that means that 3xyz is equal to 0 because a cube minus 3xyz is equal to 0, is equal to a cube. So so now product of the roots xyz taken 3 at a time is also 0. So let's try to form an equation, with roots x, y, and z, right? So the equation should be like this: t cube. What is the first term? First term will be sum of the roots. Now sum of the roots is actually a, so you should get sum of the roots is a, so you should have minus a into t square, right? Plus the next term is basically going to be sum of the roots taken 2 at a time. So but that sum is actually 0, so that will be 0 into t, and last term is going to be sum of the roots taken 3 at a time, but that sum is actually 0 again, that is 0 is equal to 0. Therefore my equation is t cube minus a t square is equal to 0, and this equation has roots x, y, z, correct? So so basically the roots of t are what? We can solve this equation directly. T square t minus a is equal to 0. So t can be 0, 0 or a, right? T can be 0, 0, a. These are the roots of x, y, and z. So we can take multiple cases. X could be 0 is equal to y and z could be a, right? That is one set of solutions. The other set of solutions is x is 0, y is a, and z is 0. And the final set of solutions is x is a and y and z is 0. So basically 3 sets of solutions for this. You have to have 2 roots 0 and 1 root a, right? So how did we do it again? So what we are doing is basically finding out what is sum of xy roots taken 2 at a time, and what is the product of xyz. All of these things we found, and then we try to get an equation whose roots are x plus y plus z. Once we are able to get the equation, we can actually directly solve that equation, and it was not very difficult there, right? So yeah, so this is solved. Now this is question number 10. Now I want to get to some other questions also, which will involve more properties that we have not yet seen. So let's look at this very typical question. Find the remainder. Find the remainder when x plus 1 power n is divided by x minus 1 whole cube. So how do you solve this type of question when you have one polynomial is being divided by something else? So what I will do here is assume x minus 1 is equal to y, right? So if x minus 1 is equal to y, x is equal to y plus 1. Therefore, my polynomial here will become y plus 1 power n, right? Therefore, it is 2 plus y power n. This is my polynomial. And what am I supposed to divide it by? I'm dividing it by y cube, right? I have to find the remainder when 2 plus y power n is divided by y cube. Great. So binomial expansion for 2 plus y power n is what? Is 2 power n plus nc1 2 power n minus 1 y power 1 plus nc2 2 power n minus 2 y square plus nc3 2 power n minus 3 y cube and so on. Notice from this term onwards, y powers will be 3 or above, right? So if I divide by y cube, I'm not, these are all terms that are divisible by y cube, divisible by y cube. So the remainder will basically be just these 3 terms, right? Remainder is going to be these 3 terms because these are not having powers of y as y cube, right? So now we just have to simplify a little. 2 power n plus nc1 is n, 2 power n minus 1. What is y? Y is basically x minus 1, correct? Plus nc2 is n into n minus 1 by 2, and 2 power n minus 2. What is y square? It is x minus 1 whole square, right? So basically, this is going to be my remainder. If you simplify it a little bit and expand it and all, you probably might, basically, why am I supposed to simplify it? Because if I want to write it as a polynomial, I should express it in ascending or descending powers of x, right? So here there is a term of x, here there will be a term of x, there will be a term of x square also, and there will be a constant term. Constant term will add with this one. So the question is now basically just writing these terms. Write these terms as a polynomial in x. So notice how we did this question. The way we did it was assumed you are dividing by something, simplified that expression by taking it as y and y cube, and then expressed the original function or the dividend in terms of y and expanded it in binomial theorem. When you do that binomial theorem expansion, you'll realize that after some point, the terms will start coming which have y power 3 and so on, powers of y which are higher, right? So that was the trick here. Let's move on. Next question for us is question 12. Solve the equation, this one. X power 4 minus 2x cube plus x square minus 2x plus 1 is equal to 0. So this is a standard trick. The reason I'm giving this question is because I want to talk about reciprocal equations. So reciprocal equations are such that the coefficients which are equidistant from both sides, the first coefficient and last coefficient, second coefficient and second last coefficient, are both equal, right? So that is a reciprocal set of equations. So here, what I will do is I will collect those coefficients together. X power 4 plus 1 minus 2 x square plus 1 plus x square is equal to 0. This is, we have collected all the coefficients which are equal together. Once you do this, you have to divide by x square. You get x square plus 1 by x square. Throughout, you divide by x square. This is a standard technique. It will be there in many books. Divide by x square, you get this. So you get 2x plus 1 by x plus 1 is equal to 0. And now you take x plus 1 by x as t. If you do that, you will get t square minus 2 for x square plus 1 by x square minus 2t plus 1 is equal to 0. And that will basically help you solve for t. So t square minus 2t minus 1 is equal to 0. You'll get t is equal to, t could be, after solving the quadratic, you will get 1 plus minus root 2. Now, if it is 1 plus root 2, then x plus 1 by x is equal to 1 plus root 2. And if it is 1 minus root 2, then x plus 1 by x is equal to 1 minus root 2. You get another 2 sets of quadratics. So this will give 2 real roots, and this will give 2 complex roots. I will leave the rest of the calculations for you. The important thing is to recognize the fact that there was a reciprocal equation. Reciprocal equations are equations where the coefficients which are equidistant from both the ends are equal. So the first coefficient was equal to the last coefficient. The second last coefficient was equal to the second coefficient from the beginning. Whenever that happens, you should collect the coefficients of the same power, same coefficients together. Collect those terms together, divide by x square. Mostly, you will get a situations like this, where either you will get x plus 1 by x is equal to t as a substitution, or maybe x minus 1 by x is equal to t as a substitution. Then solve for t, and once you get t, you have to solve another set of quadratic equations for x, right? That was simple. Then The next question is another polynomial division sort of a question. Question number 13. So let's say fx is a polynomial of degree at least 2 with integer coefficients. Find the remainder when fx is divided by x minus a and x minus b, where a is not equal to b, right? We have to find this remainder. Okay, great. So fx is a polynomial of degree at least 2, right? And the divisor polynomial has degree 2, correct? So if the divisor has degree 2, you should realize that the remainder is supposed to have degree 1 or 0, right? Remainder has to have degree lesser than divisor's degree. So therefore, remainder degree can only be 1 or 2, right? So if we assume that remainder degree can only be 1 or 0, right? So either remainder is a constant or remainder is a degree 1 polynomial. So for now, let's assume that remainder is a degree 1 polynomial, and let's say it is capital AX plus B, right? That is the remainder. So by the division algorithm, we can say f of x is equal to some quotient polynomial multiplied by the divisor plus the remainder polynomial, right? Ax plus b. This is the remainder, this is the divisor, this is the quotient, right? Now, here in this equation, if you put x is equal to a, what is you getting? F of a is equal to, this part becomes 0, and this is a plus b. And if you put x is equal to b, you get f of b is equal to a b plus b, right? Now these are two different equations. And how many unknowns do you have? You have unknown here a and unknown here b, and you have two equations, right? So you can easily solve for capital A and capital B in these two, right? How do you solve for capital A and capital B? Multiply this by small b, multiply this by small a, and subtract. So you'll get b f of a minus a f of b is equal to b minus a into capital B. So divided by b minus a is equal to capital B. So you have found this b coefficient. Once you have found this b coefficient, you can similarly find a coefficient as f of a minus f of b by a minus b. So once you have found your a coefficient and b coefficient, you have basically found the remainder polynomial, no? The other case is trivial when the remainder has degree 0. That case is trivial because that means that the polynomial here is also having degree 2 only. So that is a quadratic polynomial. So the remainder is going to be a constant. So we'll do the same thing. So you'll get plus b, and you'll put a and b, and you'll get immediately the answer. So I'm not going to discuss that case, but it is fairly straightforward. Okay, let's move on. Please keep in mind that this division lemma here and putting values a and b is a standard approach. Like, you need to be aware of this approach. You also need to be aware that if the divisor has degree 2, the remainder will have degree less than 2. So it could be 1 or 0. And I assumed an arbitrary 1 degree polynomial and found the coefficients here. Okay, let's go ahead. Question number 14. Question 14 for us is solve in real numbers. Solve in R the equation 2x power 99 plus 3x power 98 plus 2x power 97 plus 3x power 96 plus so on till 2x plus 3 is equal to 0. This is a fairly easy question, so I'll just give you a basic hint of the question. So what I will do is I'll take common here. I will take x power 98 common and I get 2x plus 3. Then this 2 I'll take x power 96 common, actually 96 common, and I'll get 2x plus 3 again, and so on. I'll keep doing it till I get 1 and 2x plus 3 here. So basically I can take 2x plus 3 common overall, and I have x power 98 plus x power 96 plus x power 94 plus so on till 1. Now this part is a GP, and the GP summation formula here gives us, actually there are 2 into 49 terms here in with x, and x power 0 to 2 into 49, so 50 terms here, right? So you'll get x power x square 50 minus 1 by x square minus 1 is the sum of the GP, and you have 2x plus 3 here. So this becomes basically 0. So you have 2x plus 3 into x power 100 minus 1 by x square minus 1 is equal to 0. That is my equation, right? So obviously this equation has one root, x is equal to minus 3 by 2. For the other roots, we cannot put x is equal to 1 and x is equal to minus 1, because that makes the denominator 0, right? If you think about it, these are all, this part has been represented like this, right? So these are all even powers. Even numbers are powers. So even if you put a negative number, it will come out positive. Therefore, this part doesn't have any real roots. The only roots that will come here will be imaginary roots. So we'll not worry about them. The solve in R was said in the question. So when we solve in R, the only possible real root for us is x is equal to minus 3 by 2. Because this expression will have only imaginary roots. So fairly straightforward question once you know how to basically take common correctly. If you're taking common correctly, you will find the answer. Okay, let's go ahead. Yeah. The next question for us is, it's an INMO question. Let's do this one. This one was question number 15 for us. Okay. Question 15, INMO. So solve the following equations for real x, y, z. Solve for real x, y, z. So we have x plus y minus z is equal to 4. X square minus y square plus z square is equal to minus 4. And xyz is equal to 6. Right? We have to solve this for real numbers. So let's look at it. Correct. So let's rewrite this equation somehow. The first equation can be written as x minus z is equal to 4 minus y. The second equation can be written as x square plus z square is equal to y square minus 4. And the third equation can be written as xz is equal to 6 by y. So what am I doing? Think about it. I'm just isolating x and z here, x and z here, x and z here, and y on the other side, right? Now we have an identity that says x minus z whole square plus 2xz is equal to x square plus z square, right? So that will help us eliminate x and z, right, from these equations, because we'll get an equation in terms of just y. So what I'm doing is eliminating x and z. So I'll do x minus z whole square, I'll write as 4 minus y whole square plus 2xz I will write as 2 times 6 by y is equal to x square plus z square is equal to y square minus 4, right? Great. So what I get is y into 4 minus y whole square plus 12 is equal to y into y square minus 4, right? So simplifying this, we get y cube plus 16y minus 8y into minus 8y square plus 12 is equal to y cube minus 4y. So y cube gets cancelled and you end up getting 8y square minus 20y minus 12 is 0. So that becomes 2y square minus 5y minus 3 is equal to 0. So that can be easily solved. Y will become minus half or 3. Y is becoming minus half or 3. If y is equal to minus half, then you get xz is equal to, basically xz is coming out to be 6 by minus half, so minus 12, but x square plus z square is coming out to be 1 by 4 minus 4, right? So negative 15 by 4, which is not possible for real numbers. So basically, if I take y as a minus half, then I'm not able to solve in real numbers, right? So I'll take y is equal to 3, and that will give me x square plus z square is equal to 9 minus 4, 5, and xz is equal to 2, right? 6 by 3. So this equation correct. This equation has a clear solution. You can put x is equal to 2 and z is equal to 1 and y is equal to 3. Or you can also do x is equal to 1 and z is equal to 2, right? You can even do minus 1 and minus 2 for x and z. So now you are getting multiple solutions. You can get x is equal to 1. No, x is equal to 2, y is equal to 3, z is equal to 1. Also get x is equal to minus 1, y is equal to 3, and z is equal to minus 2. These solutions you are definitely getting. You can exchange x and z also, that is also fine, I think. And that is your solution for the problem. So notice that if you do anything else, right? If you do any other step other than these steps, the question might become complicated. Because this step, what I'm doing is I'm putting x and z on one side and y on the other side. And later I'm eliminating this by this identity. What am I eliminating? I'm removing x and z, because I'll write, instead of this, I'll write y square. Instead of this, I'll write this. Instead of this, I'll write this. So you will end up getting a one equation in one unknown, which is much better, right? So that is a nice way to solve this one. Okay. The next question. The next question that I will look at is another INMO question. The question is, prove that if the coefficients of the quadratic equation ax square plus bx plus c is equal to 0 are odd integers, then the roots of the equation cannot be rational numbers. The question is, if the coefficients of this quadratic are odd integers, then the roots cannot be rational numbers. Okay, so let's say, suppose we have a rational root p by q where p and q are co-prime. P and q are co-prime. We have a rational root p by q of this quadratic. So we should have a into p by q whole square plus b into p by q plus c is equal to 0, right? So therefore that becomes ap square plus bpq plus cq square is equal to 0, right? This is my equation. Now, okay, now if the coefficients of the quadratic are odd, we have to prove that roots cannot be rational. Correct. So let's think about what are the cases for P and Q. So if P and Q are both odd, if P and Q are both odd, then all the terms of this equation will be odd, right? Because you will have A is odd, this 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 is odd. So you have odd plus odd plus odd, right? So then this will give an odd number, right? This will give an odd number and it cannot be 0 then, right? Expression will not be able to be equal to 0 even if A, B, C are negative, because 0 is even. 0 is considered an even number. So you cannot add 3 odd numbers and get 0. Why? Because the difference of 2 odd numbers is even, right? So think about it, 3 odd numbers can never be summed up to 0. So if P and Q are both odd, then there is a contradiction. Correct? Let's think of the case when one of them is odd, one of them is even. So P is, let's say P is odd, Q is even, right? P is odd, Q is even. So A is odd, P is odd. So this part is odd. B is odd, P is odd, but Q is even. So this is even. And this is odd because Q, no, this is also even. Q is even. So Q square, this is even. So you have 2 even numbers and 1 odd number. 2 even numbers will give an even number here. Even number plus odd number can never be 0, right? So this part is also giving us a contradiction. Now, if you take P and Q both even, then you are getting again even, sum of 3 even numbers, right? Oh, actually P and Q cannot both be even anyway, because P by Q is supposed to be co-prime, right? P and Q are co-prime. So you cannot even have this case, you cannot have this case, and you cannot have this case. We are getting a contradiction in all 3 cases if you assume P by Q is a root of this equation. The first 2 contradictions were happening because we are saying that sum of even and odd numbers cannot give 0, and also sum of 3 odd numbers cannot be 0, right? So we have proved by contradiction that this is not going to be possible. Okay, then the next question that we'll look at is, these are all INMO questions, by the way. The next question here that we'll look at is prove that the polynomial f of x is equal to x power 4 plus 26x square plus 52x, 26x cube it was. I think so. One second, let me check once. Okay, I think there is a slight confusion in the question here, so I'll just not use this question. Let's go to a different one. Okay, let's do this one. Let ABCD be 4 real numbers, not all equal to 0. Not all equal to 0. Prove that the zeros of the polynomial f of x is equal to x power 6 plus ax cube plus bx square plus cx plus d cannot all be real. Okay, so A, B, C, D are basically 4 real numbers, not all equal to 0, such that we have this polynomial f of x is equal to x power 6 plus ax cube plus bx square plus cx plus d, right? Now, we have to prove that all the roots of the polynomial cannot all be real. So let us suppose the opposite. Let us suppose that all roots are real. All roots are real. And let's call these roots alpha, beta, gamma, delta, this symbol and mu, right? These are my roots. So basically, if you do Vieta's relations here, you will get sum of the roots 1 at a time should be 0 because x power 5 is not there. Sum of the roots 2 at a time should also be 0 because x power 4 is not there. Sum of the roots 3 at a time, right? Minus plus minus. So it is minus a and so on. Now we'll get terms. So because this is 0 and this is 0, we can say that sum of the roots, square of the roots is equal to sum of the roots alpha whole square minus 2 summation alpha beta. But this is 0 and this is 0, right? So we are getting sum of alpha square is 0, right? Now what does that mean? That means that alpha square plus beta square plus gamma square plus so on, all 6 roots, right? The square of them is adding up to 0, and if they are all real numbers, then each of them must be 0, right? Only if sum of squares are being added and they are all real numbers, then each root is 0 now. If each root is 0, then you must have all of these products, everything is 0. So basically A should be 0, B should be 0, C should be 0, and D should be 0, right? Because sum of the product of the roots taken 3 at a time will be 0, 4 at a time will be 0, 5 at a time will be 0, and 6 at a time will also be 0. So if you suppose that all the roots are real, you are getting the result that A is equal to B is equal to C is equal to D is equal to 0, which is a contradiction to the problem statement, which says that not all equal to 0. Hence, we have a proof by contradiction here, and we have gotten our answer, right? Okay, so that was interesting. Then let's look at a very famous question. Question number 18. This is INMO again, INMO 1986. So this is if Px is a polynomial, Px is a polynomial with integer coefficients, and a comma b comma c are 3 distinct integers, then show that it is impossible to have P of A is equal to B, P of B is equal to C, and P of C is equal to A. Show that this is impossible, right? So we'll again prove by contradiction. We'll say, suppose it is possible that P of A is equal to B, P of B is equal to C, and P of C is equal to A. So now think about it. We have, let's look at the polynomial P of X minus P of B. Let's look at this polynomial. We know that this polynomial vanishes at x is equal to b. Why? If you put x is equal to b in this polynomial, it will be P of B minus P of B, which is 0, right? So therefore, we can say by factor theorem, x minus b is a factor of x minus b is a factor of P of x minus P of B, right? Correct. So x minus b is a factor of this. Therefore, if I put the value of x is a, so we should get a minus b is a factor of P of a minus P of b, right? Correct. Similarly, exactly same way, you can prove that b minus, oh wait, 1 second. So P of a minus P of b is what? P of a minus P of b is actually b minus c, right? We have gotten a minus b divides b minus c, right? This is what we have gotten. A minus b is a factor of P of a minus P of b, which is b minus c. In a similar way, we can prove the opposite also. We can say b minus c is a factor of P of a minus P of b. The opposite, basically. We can say that P of a minus P of b b minus c is a factor of a minus b. I want to get a minus b here, so I should write P of c minus P of a, right? P of c minus P of a. So my polynomial was P of x minus P of a, and in that I am saying a is a x minus a is a factor. X minus a is a factor of P of x minus P of a. So then putting c, no, x minus c is a factor, we have to say. Okay, I'm getting a little confused here. 1 second. So what we have proved so far is a minus b is a factor of P of a minus P of b, right? What I want to prove is b minus c is a factor of a minus b. B minus c is a factor of a minus b. Yeah. By that, I will get the proof that a minus b is equal to b minus c. So I will follow the same exact steps. I'll follow the same exact steps and try to rework it. So I want to have b minus c. I want to prove b minus c is a factor of a minus b, right? B minus c is a factor of a minus b. And what is a minus b for us? A minus b is the same as P of c minus P of a, right? P of c minus P of a, correct. So what I want to get is this is b is actually a value that I put. So I can say x minus c is a factor of P of x minus P of a, and okay, I should put basically I should put x minus b is a factor of this, and I will put x is equal to c. If I put x is equal to c, I will get c minus b is a factor of pc minus pa, and pc is equal to a, and pb is equal to c. Pa is equal to b and pc is equal to a. So I'll get a minus b here, and I'll get c minus b here, right? So basically, I was just working out the implications. So if I have px minus pb vanishes at x is equal to b, so I have x minus b is a factor of this. That means this is a general statement for all x, so I can put x is equal to a here, putting x is equal to a here. And I get a minus b is a factor of this, and pa minus pp is b minus c. Now I'm just doing the opposite thing. I want b minus c is a factor of this. So what I'm saying is a minus b is what? Pc minus pa, right? A minus b is pc minus pa because pc is a, pa is b, right? So instead of c, I'll put x, so px minus pa, and I have to put c somewhere. So here I will put x minus b as my variable, and if I put c, I'll get c minus b is a factor of this. So c minus b is a factor of a minus b I'm getting, which implies that this is a factor of this and this is a factor of this. So therefore I should have a minus b is equal to plus minus b minus c, right? Correct. Now let's go ahead in the next screen. So since a, b, c are all distinct, since a, b, c are all distinct, therefore we cannot have b minus c is equal to minus of a minus b, because that will mean what? It will become minus a plus b, and b will cancel, and you'll get a is equal to c. So that is an impossibility. Therefore, b minus c must be equal to a minus b only, right? This means that b is equal to half of a plus c, right? B is equal to half of a plus c. That means b lies between a and c. This means that b lies between a and c. Okay, so we have concluded that b lies between a and c. Similarly, repeating the argument just for a different variable, we can also conclude that c lies between a and b. In the same way, we can conclude this also, which will be an obvious contradiction, which will be a contradiction. See, here there was nothing special about us choosing b and a and c, right? Here we chose prove that a and c, b lies between them. But a and b and c were arbitrary. I could have done the simple, the same proof with different variables, and you would have gotten c lies between a and b, right? It is obvious then that these two things cannot happen at the same time. Hence, what we assumed that PA is equal to B, PB is equal to C, and PC is equal to A. These three things cannot be true simultaneously. Cannot be true simultaneously. As long as A, B, C are distinct integers, right? Correct. So that is the proof. There was a similar question in INMO 1992 that was also very similar, but that used a little bit more advanced knowledge. It was using pigeonhole principle. We probably might discuss it in a future video. So I hope this video where we did around 19-20 questions and we also looked at a few theorems, I hope this will be useful for you. What you should go ahead and do now is solve questions from past RMO papers, past RMO, INMO papers, all sorts of equation questions you should be now able to attempt. Go through this video in detail, go through it with a pen and paper in hand, pause the video, look at the questions, try your solutions yourself, and then proceed ahead. So this covers mostly all of the ideas of solutions that you would probably encounter at least till the INMO level. So in the future videos in this course, what I'll be doing is
doing slightly more advanced problems and slightly more advanced theorems, especially about polynomials, which will be more useful towards a INMO or International Maths Olympiad sort of a competition level. But you don't have to worry. We'll cover it from the basics, and hopefully you'll get the ideas there as well. For now, revisit this video with pen and paper in hand and basically make the best use of it. Solve these problems yourself. These ideas are very crucial as you go ahead and try to solve equations problems. So that's all for this video. I'll see you next time. Stay tuned for more videos on other courses as well. And please like, share, subscribe to the channel. I need 600 subscribers so that I can launch my next course soon. We are on 530 right now. So I'm looking forward to your support and looking forward to providing more amazing content for you guys. See you next time.